Good day. Welcome to the Physics Exercises channel. Today, I will talk about two of the interesting effects of special relativity, one of which is time dilation. And the other is Lorentz contraction. Okay? So these are both effects which are in special relativity. And before starting their derivation, which is what I'm going to do here, let me just state that special relativity, which are sometimes abbreviated as SR. So SR has two postulates. SR1 is that the laws of physics are the same in all inertial reference frames. Inertial reference frames. Okay, and I'm going to abbreviate inertial reference frames as IRF. That's the first postulate. The second postulate is that the speed of light which I will always use the notation c for the speed of light, is the same in all ref frames. Okay, so the speed of light is a constant. It's a universal constant. Okay, and what I want to now talk about is what kinds of effects these two postulates lead to. Okay, so we postulate these two, and we will study two effects, and one of them is time dilation, and the other is Lorentz contraction. Okay, so let's focus first on time dilation. Okay, and time dilation refers to the following effect. If there's an observer, let's say, okay, let's take as an example a train or a bus, doesn't matter. Okay, and there's a passenger on the bus, and the bus moves with velocity v in some direction. Okay, and let's call this okay, the bus. Okay, so that's going to be the so that's a reference frame now. Okay, what I mean by B is a reference frame, which is the bus. But there's also a guy standing at the station. Okay, so, and obviously they have two different but inertial reference frames. Okay, so B and S are both IRFs, inertial reference frames. Sorry, let me erase. I'm going to abbreviate it, but I forgot that I was going to abbreviate it. Okay, so both of these are IRFs. Okay, and time dilation refers to the following. Suppose that there are two events which take place, and the time difference between the two events is measured by the guy on the bus and the guy at the station, i.e. in two different inertial reference frames. Okay, and the statement is that the time interval measured on the bus is not equal to the time interval measured at the station. Okay, whereas this, according to the previous version of mechanics that existed before special relativity, in Galilean relativity, the two time intervals would be the same. But because of special relativity, primarily because of the constancy of the speed of light, these two time intervals are not the same. Okay, we're going to prove it, and we're going to derive the relations between them. Okay, so let's go and now imagine almost the same experiment, okay, but with a little bit of modification. So again, I have my bus. Okay, and I have the guy on the bus. And the following experiment occurs. A light source emits some light, which goes up and goes back down. Okay, so here we have a light source. Okay, and it emits light, goes up and comes back down. And let us also assume that the height of the bus is h. Okay, the height of, we take the height of the bus to be h. Okay, and let us first calculate delta TB, which I'm going to say that the interval delta TB is for the light to go up and back down. So light goes up and back down. Okay, and we can easily see that in this particular reference frame, so it's just two vertical trips. Okay, so this guy is sitting here and sees, well, I drew him that he's turning this way, but if he turns around, he will see that the light goes up and back down, and these are vertical trips. Okay, so one up and one back down. So we can actually calculate delta TB as h divided by c and multiply that by 2. Okay, so that is our time interval as measured by the person on the bus. And now I have to draw things slightly different because we want to get an idea of what happens or what is seen by the person at the station. Okay, so, but we should keep that result handy. Okay, so here again, I will draw, you know what, I'll use colors. Okay, so let's say the bus starts at some point. Okay, so I'm going to use red color. So here's the bus. Here's the bus when the light is emitted. Okay, and the bus, what it will do is move to a different position. So I'm going to draw that in black. I'm going to try to draw that in black. Okay, so here's again our bus. Okay, so what happened is that our bus moved, and of course the distance by which it must have moved is v delta t. Okay, we have to take this into account. And let me actually, okay, let me try to get a drawing, and I draw the person at the station, because now we're considering the inertial reference frame of this person, so the person at the station. And let me actually try to draw here the light source. And what has the light done in between? Let's find a nice color for that, maybe yellow, okay? The light has done this. Okay, sorry, let me redo that because it's not a nice straight line. Okay, but from the point of what this person is seeing, the person at the station, is that the light, let me try to, okay, maybe this is about halfway between these things. So the light goes up and the light comes back down. Okay, and they are both straight lines. Okay, now I go back to black color and again indicate that this height is h. Okay, and the point is that now, so the light will travel still at velocity c. Okay, so let's just go back to the previous part of the example. So when we were doing this, the light went up with velocity c, and the distance it covered is h. So it must have spent, the time it must have spent is h over c one way and h over c the other way too. Okay, so that's how we got this delta be h over c. But what happens here is actually slightly different, because here what we have to take into account that there's actually a right triangle here. Okay, and one side of that right triangle is H, and the other side of that right triangle is V delta T squared. And that must be equal to C squared delta T squared, because C is the velocity of the light, and delta T, if you multiply C by delta T, that must be the length of the path that the light has traveled. Okay, so, and sorry, I should indicate that these are in the reference frame of the guy at the station. Okay, so this is actually the main equation we will use to figure out delta TS. And if we rearrange this a bit, so we will get H squared is equal to C squared minus V squared delta TS squared. But that's actually just one way. Okay, so this is actually just one way. We will have to multiply by 2 at the end. Okay, so this is what I'm calculating here. Let me make a distinct notation. Let me put a bar over it. Okay, and by bar, I mean delta S is equal to twice delta TS bar, because this equation, the way I've written it, considers only part 1 when the light goes upwards. But part down obviously has to be the same, because the light is going to reflect on a mirror and come back the same way. Okay, and now what we can say is that our delta TS prime is equal to H over C 1 minus V squared over C squared square root. All I did was just a little bit of algebra, a little bit of rearrangement. And we see that delta TS is equal to twice H over C, 1 minus V squared over C squared to the power 1/2. And this, if we go back to delta TB, we remember that delta TB took the form 2H over C, which means that we can write delta TS as delta TB divided by, scroll up a bit, 1 minus V squared over C squared, which actually can also be written as gamma delta TB, where gamma, since this is so often used in special relativity, that this variable here has a special symbol for it. Okay, so what we found is that delta TS is equal to delta TB divided by the square root of 1 minus V squared divided by C squared. Okay, so this is the equation which characterizes time dilation. Okay, and what it states is that in different reference frames, which move at different velocities with respect to each other, well, in this case, in particular, one of our reference frames was the one which is not moving, right? So the bus reference frame was the one in which there was no displacement in the horizontal direction. Okay, so at least in this particular case, when we have these two reference frames, one moving with velocity v with respect to the other, we can relate time intervals between events with this equation. Delta TS is equal to delta TB divided by 1 minus V squared over C squared square root. Alternatively, we can write it as delta TS is equal to gamma delta TB. Okay, now let us investigate gamma a little bit. Okay, so gamma is 1 divided by square root of 1 minus V squared over C squared. In most realistic situations, most everyday situations, the velocity v, velocity of the bus, of course, is going to be much, much smaller than the speed of light. Okay, so this means that in this case, gamma tends to 1, and we recover the Galilean result, okay, in which, so in this case, the two observers in the different reference frames will be measuring the same time between the two events. Okay, on the other hand, there's something else that we can see here, that V is always smaller or equal to, if we are talking about light, but okay, so we should probably just say V is, for massive objects, V is smaller than C. V is smaller than C, which means that gamma is going to be, well, here we have V over C is smaller than 1. So 1 minus a number smaller than 1 is going to make the square root smaller than 1, which means that gamma is actually going to be greater than 1. Okay, and what this means is that if we are in the reference frame of the bus, then that's actually the maximum time. Right? Sorry, that's the minimum time. Okay, so that's the minimum time because gamma is always, gamma for any finite v is always greater than 1. Okay, so, so it means that delta ts is equal to gamma delta tb. Okay, but the faster the velocity is, the bigger this delta ts will become. Okay, so the longer this delta ts will become. Okay, and actually, this is the basis of the so-called twin paradox. And the twin paradox, which turned out to be not really a good example of a paradox for various technical reasons, such as turning a spaceship around and stuff like this. But let's just sort of try to recap it, because sometimes these thought experiments do give insight, physical insight. The point is, if you have two twins, okay, so here you have two persons who are twins, and one of them flies away on a spaceship. Okay, in that case, time will pass faster for this person than for this person, and this the person who's staying on the ground will age more in a given time interval. The real twin paradox says, okay, spaceship goes for many, many years, comes back, and this particular twin, let's call this twin 1 and this twin 2. This twin 2 is young, this twin 1 is actually very old. And this actually is not really a reproducible experiment because there's several issues here, namely that the spaceship actually has to turn around, okay? But in any case, for the straight path that you consider, if you just consider this straight path, it will hold in general that the twin that stayed on the ground will actually age more than the twin that goes away in the spaceship. Okay, so we derived this, and let's keep it in mind. Delta Ts is equal to gamma delta Tb. Okay, and let us now go to our second example, which is the so-called Lorentz contraction. Okay. Okay, and what Lorentz contraction refers to, is, suppose that we have a ruler, okay, and it has some length L, which we wish to measure. And we can consider two cases. We will consider two cases here. In one case, the person measuring the ruler will be traveling at the same speed as the ruler. Alternatively stated, the person will not see the ruler growing at any velocity. Okay, so here's the person, okay, and he's measuring the ruler somehow. Okay, and this person will measure some length L. But suppose that there's another experiment where there's another person, let's say here, And compared to this person, the ruler is moving with velocity v. Okay, and this other person will measure some other value lambda prime, L prime for the length of the ruler. Okay, so that's the statement, that's the phenomenon, Lorentz contraction. And now what we want to do is derive Lorentz contraction. And we're going to go back to the same example, and we're going to use the bus again. Okay, so the bus again. Let me draw the bus. And the experiment will be the following. Okay, so the bus, here's our bus. Here we put a light source at the back of the bus. Here's the guys on the bus. And what we're going to do is emit some light this way. It hits a mirror in the center of the, in the beginning, at the front of the bus. And then the light goes back the same way. Okay? And let us say that this, sorry, I wanted to make this black. This is going to be the length that we are concerned with. And there's a length in the reference frame that we call the reference frame of the bus. And again, there's guy at the station, and there's a length which is LS, the length measured by the guy at the station, and the two are not equal in general. Okay, so two are not equal. Okay, and we can analyze this by very similar means to the previous example, to the time dilation example. Okay, and I have to draw again the bus in two different ways. Okay, I'm going to redraw the bus again the same way. Okay, because I want to really go step by step. So here, so the bus even is moving. So here's the bus. So the bus may be moving, and the light is emitted, and the light is sent back. And what we can say, and we'll state it as follows. We have delta T1, okay? Actually, it's a delta T1. Okay, I'm going to say in the bus reference frame. Okay, so delta T1 in the bus reference frame. Let's say for now I'm working in the bus reference frame, so I'm not going to indicate that as an index or something. But delta T1 is going to be LB divided by C, and delta T2 is going to be again LB divided by C. Okay, and delta T2 is the trip back for the light. Okay, so the total delta T on the bus is 2LB divided by C. 2LB divided by C. Okay, so that's one equation that we're going to need. And now let's draw the bus again. Okay, but let's try to draw it in such a way that what the guy at the station would see. Okay, and sorry, I didn't mean to do that. Let's draw a red bus for the bus that was in the past, so to speak. Okay, so this is the starting bus. Okay, and let's draw the bus at a later time, just to indicate what is going on. But first I'm going to change the color back to black. So at a later time, oh, sorry. So at a later time, our bus might be maybe here. Not a great drawing, but sorry about that. And now we draw the light, because what happens to the light? The light is emitted, okay? And it goes all the way to the front of the bus, but the bus moved in the meantime. Okay? So that's part one of the trip. That's part one. And actually, we can draw part two of the trip. So let me go back to black. So let's do a part two of the trip. Here's our bus again. Okay, but our bus will move. So I'm going to indicate that the moved bus in this case by blue. And in this case, if we want to draw the light properly, it starts here when the bus, so notice that the black bus is the intermediate bus, so to speak. And here the light is emitted and it reaches the back of the bus, but the bus has moved. So the light is now going this way. But in all of this, the bus, of course, is going with velocity v that way in both examples, velocity v that way. Okay, and now we're going to assume that the length measured by the guy at the station, so the length of the bus as measured by the guy at the station, we're going to take that to be ls. Okay, so this length here is ls. Okay, and then we do very similar to above. We're going to calculate the time that it takes. Okay, so now I'm at the station, this particular reference frame. And what I'm going to say is that for the first process, this is the first process. Let me show it again. Okay, that's the first process. So for the first process, the time it took is going to be, well, it's going to be ls divided by c plus v delta t1 divided by c. Okay, so I'm also making the assumption that this first process here took delta t1 that much time. Okay, and of course the second process, just to keep the notation consistent, I'm going to assume that it takes delta t2 for the second process. And for delta t2, we can say lsc, but now they're going in the opposite direction, minus v delta t2 divided by c. Okay, and now we have to do a little bit of algebra. Okay, and the way I prefer to do this is to multiply. So I'm going to take this equation and multiply it by c. And multiply this one also by c. Okay, so then my equation becomes, so I'm not doing just math. Okay, so c delta t1 is equal to ls plus v delta t1. And my second equation becomes c delta t2 equals ls minus v delta t2. So I will keep working with this delta t1 and delta t2. So I have actually delta t1 is equal to ls divided by c minus v. And my delta t2 is going to be ls divided by c plus v. Okay, when I rearrange these equations and I express delta t1 from the first equation and delta t2 from the second equation. And then I can say that the total time as measured by the guy at the station is ls divided by c minus v plus ls divided by c plus v. And we can actually work a little bit further, because we can say that this is c squared minus v squared ls times 2c, right? So if I, here in the numerator, I have to add c plus v plus c minus v, and this gives me 2c. So what results here is that delta Ts is equal to 2lsc divided by c squared minus v squared. Let me rewrite that slightly differently. It's actually 2ls divided by c1 divided by 1 minus v squared over c squared. Okay, so I just rearranged this slightly. Okay, and what I actually want here is to relate lengths, not times. We already did that. Okay, so we already did relate times, and we found that delta Ts is equal to gamma delta Tb. Okay, so one thing we can do here is to immediately say that delta Ts is gamma delta Tb, and remember that that was actually delta Tb divided by square root of 1 minus v squared over c squared, right? So if delta Ts is gamma delta Tb, then first we can actually write that so I'm going to substitute for this delta Ts from this equation. And I see that I can cancel a 1 minus v squared over c squared. So this is actually gamma 2ls divided by c. Okay, so that's what we have. Delta Tb is gamma 2ls divided by c. But let's go back to the previous equation that we found for the guy on the bus. We found for the guy on the bus that delta Tb is 2lb over c. So this is also 2lb over c. Okay, so our lb is going to be gamma ls. Okay, and that's the equation for the Lorentz contraction. Remember, this equation here is the time dilation equation. This is the Lorentz contraction equation. So gamma 1 divided by 1 minus v squared over c squared. And let us see why this is a contraction equation. To see that, it's actually easier if we write ls as square root of 1 minus v squared over c squared times lb. Okay, that's the same Lorentz contraction equation. The length measured by the person on the bus, which is the inertial reference frame in which the object is stationary, is actually the so v equals 0. That's the maximum this ls can be. Okay, and so lb is some number, and it's multiplied by a number that is smaller than 1. So ls is going to be smaller than lb for at finite velocities. Let me write it like this, at finite v. Because at finite v, square root of 1 minus v squared over c squared is smaller than 1. It's important to note that this is also, it's somewhere between 0 and 1, okay? And this means that the guy at the station will measure the same object to be slightly shorter, shorter by this factor of square root of 1 minus v squared over c squared, than the guy on the bus will measure for the same length. Okay, so this is the idea of Lorentz contraction. So these are the derivations, and probably in subsequent videos, I will discuss this in more detail, especially what we mean by measurement in special relativity.